The game chess is one of the oldest and most popular board games in the world. It's a two-player game where each player controls 16 distinct pieces, each of which can only move according to very specific movement rules. In this video we will primarily focus on one specific piece, called knight. The knight follows a very interesting movement rule. It can move in what are called L-shaped moves, meaning it can only move 2 squares in one direction and then 1 square perpendicular to that. An interesting and very old question regarding the knight is whether it can start at an arbitrary square and then visit all squares on the chessboard exactly once. Such a sequence of moves by the knight on a chessboard is called a knight's tour. In the main part of this video we will deal with the question of how a knight's tour can actually be created and why it seems to be so difficult to find one. And in the center of this video, of course, is the connection of this problem to graph theory. The knight's tour in the animation is essentially a directed knight's tour. It's important to note that with every directed knight's tour, one obtains also the reverse directed knight's tour for free. In the case that the knight's tour is not restricted to any specific direction, it is called an undirected knight's tour. Regarding the notation in this context, it is common to represent moves with arrows or lines as shown previously. It is also common to place a small dot on every visited square. Personally, I prefer a notation where the dots are numbered in the order they have been visited, or simply a notation with the numbers in the corresponding squares. Before we start investigating this problem, let me introduce you to 3 kinds of knight's tours that you should be aware of. The first knight's tour is one that starts at a particular square and ends on a square that is not a knight's move away from the starting square. This type of tour is called an open knight's tour. And if there are open knight's tours, then there are probably also closed ones, as you can see in the second animation. In this video, a knight's tour is considered closed if the knight moves actually back to the starting square at the end of its tour. Another very interesting knight's tour is the one next to the closed knight's tour. Summing up the numbers in all rows and columns yields always the same number, 252. Such a knight's tour is known as a magic knight's tour. Very important for the understanding of the enormous complexity of this problem are the numbers of directed knight's tours on an n×n chessboard, and trust me, those numbers will probably blow your mind. The amount of different combinations to create a knight's tour on larger chessboards is simply incredible. Considering this, it is no surprise that there is a knight's tour on an 8×8 board starting from any position. But even though there are many knight's tours, finding one is very challenging, as we will see later in this video. Now where's the connection between this problem and graph theory? I wouldn't say it's just this problem that has a connection to graph theory. It's the game of chess itself. Regarding the movement rules of the 6 chess pieces, they can be used to construct chess graphs, such as the pawns, kings, knights, bishops, rooks and queens graph. And the construction of those graphs is basically very straightforward. We simply take a specific chess piece and place it somewhere on the chessboard. Every square represents now a node, and 2 nodes will only be connected with each other if the chess piece can move between them. Once this process has been repeated from all squares, we obtain the chess graph associated with the corresponding chess piece. Especially the knights, rooks and queens graph are very interesting from a graph theoretical perspective. The queen's graph appears, for example, in another famous chess problem, the n-queens problem. This problem involves placing n queens on an n×n chessboard so that no 2 queens threaten each other. Therefore, a solution requires that no two queens share the same row, column, or diagonal. This is in fact also a quite challenging problem, especially on large chessboards. Considering a solution for this problem on a relatively small chessboard, let's say on a 4x4 board, one can view this positioning from a graph theoretical perspective by investigating the corresponding queen's graph and coloring the nodes that represent the squares where the queens are located. The set of colored nodes describes now a specific set of nodes that appears quite often in graph theory. This here is a maximally independent set of nodes in the 4x4 queen's graph. But what exactly is an independent set of nodes in a graph? An independent or stable set is a set of nodes in a graph such that no two of which are adjacent. A maximal independent set is then an independent set that is not a proper subset of any other independent set. So in summary, you can remember that if you color some nodes in a graph with one specific color and none of the colored nodes are connected to each other, then they describe an independent set of nodes in the corresponding graph. Now, what exactly is a Knight's Tour from a graph theoretical perspective? An open or closed Knight's Tour on a chessboard translates to a path or cycle in the corresponding Knight's graph that visits each node exactly once. Furthermore, such paths or cycles have also their own names. They are called Hamilton paths or cycles, named after the mathematician Sir William Rowan Hamilton. Altogether, you should remember that an open Knight's Tour on a chessboard is essentially a Hamilton path, and a closed Knight's Tour a Hamilton cycle in the Knight's graph. We aim now to derive an algorithm to compute a Hamilton path in the Knight's graph. In this context, we will also be confronted with the algorithm for finding such a path in a general graph. You can think about an algorithm as a recipe, nothing else than a list of instructions for solving a problem, in this case a computational problem. If there is a solution for a computational problem, then we say that an algorithm solves this problem if it terminates in finite time and if it returns a correct solution. Algorithms appear in many contexts, whether it's for sorting, computing Euler circuits, Hamilton paths, etc. Very important in mathematics are so-called decision problems. These are problems where a specific question regarding a computational problem serves as input for a specific decision algorithm that provides an answer that is either yes or no. As an example, one can consider the decision version of the Hamilton path problem, which consists of the question whether a graph contains a Hamilton path. The problem here is not to compute a Hamilton path for the input graph, but rather to decide if such a path even exists. Nevertheless, it should be clear that one can also answer this question by checking all possible paths in the input graph, defining a valid decision algorithm for this problem. If the algorithm finds then a Hamilton path, then it returns yes. Otherwise, it returns no. In general, one would search here for a decision algorithm that returns a solution as quickly as possible. And even though there might be a better way here to decide whether a graph contains a Hamilton path, its overall efficiency is still not satisfactory. But more about this in a moment. Regarding a decision problem, one can also analyze the complexity required to verify a yes instance of the underlying problem. Let us take a yes instance of our previously discussed decision problem, the Hamilton path problem, as an example here. The main question is now, how quickly can we verify that the given Hamilton path is indeed a Hamilton path for the underlying graph? Unlike the decision question of whether a graph contains a Hamilton path, verifying whether a given path actually is a Hamilton path is much simpler. Because the only tasks involved here are to check that the path is indeed a path and that it visits all nodes of the graph. You see, the question of the efficiency of decision and verification algorithms seems to be important. Furthermore, analyzing other decision problems in this manner allows us then to classify them in terms of their complexity. We can compare, for instance, the decision problem of whether a graph has a Hamilton path with the decision problem of whether a graph has an Euler trail. While both problems may sound similar because they focus on walks visiting each node, Hamilton, or edge, Euler, exactly once, they differ enormously in terms of their complexity. In fact, they belong to totally different complexity classes. The decision problem of finding an Euler trail, for instance, belongs to the complexity class P, where P stands for polynomial time. All decision problems in the complexity class P can be solved and verified in polynomial time. Solving a problem in polynomial time is generally considered quick. The set P is then obviously a subset of the set of problems whose solution can be verified in polynomial time, but which do not necessarily have to be solvable in polynomial time. This class is called NP. The hardest decision problems are contained in the complexity class NP-hard. The problems in this class are at least as difficult or time-consuming to solve as the hardest problems in NP. Solutions to NP-hard problems are not necessarily verifiable in polynomial time, and some of these problems may not even be decidable. And then there is also a very special complexity class called NP-complete. This class lies in the intersection of NP and NP-hard and contains therefore problems whose solution can be verified in polynomial time, but which are probably not solvable that quickly. Furthermore, the problems in this class can be reduced to each other, and although it may sound surprising, solving any one of these problems in polynomial time would imply that all problems in NP can be solved in polynomial time, which is very likely not possible. Also, the Hamilton path problem is NP-complete, and given the assumption that P is not equal to NP, we cannot expect to solve this decision problem quickly on an arbitrary graph. But be aware of the fact that no mathematical proof has been provided yet to show why P is not equal to NP. This remains a widely held assumption, and it is essentially one of the biggest open questions in mathematics. In the following we will go through several approaches to solve the Knight's Tour problem, or in other words the Hamilton path problem on the Knight's graph. The first approach involves a brute force algorithm, an algorithm that generates random tours until a generated tour is a Knight's Tour. The efficiency of a brute force algorithm depends obviously on the number of possible tours on the chessboard. But let us be honest, this does not sound very promising even on a smaller chessboard. Some tours generated by the brute force algorithm can be over very quickly, while there can also be tours where only one square remains to visit at the end. And even if only one square is missing at the end, this does not imply that the tour was close to a Knight's Tour. In fact, the move that eliminates the possibility of achieving a Knight's Tour occurs quite often right at the beginning of the tour. Here I conducted a small empirical experiment to demonstrate the inefficiency of this approach. I randomly generated 1000 different tours on a 5x5 board and counted how many of them turned out to actually be a Knight's Tour. Now what do you think? After how many attempts did the first Knight's Tour occur? The first Knight's Tour occurred actually at attempt number 467. And unfortunately this was also the only Knight's Tour. I think it's not difficult to see that the probability of finding a Knight's Tour in this way on a larger chessboard approaches 0. Furthermore, a large chessboard makes it also nearly impossible to track already visited tours due to a computer's limited memory. The natural way to solve the Knight's Tour problem is with a backtracking algorithm. Backtracking is in fact also an approach that involves trying all possible tours in the worst case, but in a much more logical and systematic way than the brute force approach. If a tour fails due to a few unlucky moves whose correction could easily result in a Knight's Tour, these potential corrections are not considered in subsequent attempts. And this is exactly where backtracking comes into play. Let's say we start with a random tour on our board. As we know by now, the tour will very likely end in a dead end. That is a square from which there is no follow-up move anymore. And once we are stuck, there is basically only one logical way to continue without generating a totally new tour. The name explains it already. The idea is to go back to the previous square of our tour, and to remove the indication that the red square has been visited. The algorithm will never allow to move to the above square again in exactly this path constellation. From the knight's current position, we can explore now other paths with the hope of finding a knight's tour. Anytime we reach a dead end, we move with the knight back to its previous position and go to a different square. The rest of the animation takes actually way too long to be shown in the video. Additionally, it is hard to follow the steps if the video is speed up too much. For this reason, I want to demonstrate the backtracking procedure first on two relatively small graphs, before showing you a speed up version of the backtracking algorithm on the knight's graph of a 5x5 chessboard. It's important to note that a backtracking algorithm is the typical way to compute a Hamilton path if one exists. The algorithm systematically tries to compute a Hamilton path from all nodes until it finds one. If it does not find any Hamilton path in the corresponding graph, then such a path does not exist. In our graph, the algorithm will start with the node 1. And if you look closely, you will notice that there cannot be a Hamilton path starting from exactly this node. But it's still a good exercise to see how the algorithm works. Since the algorithm does not know yet that there's no Hamilton path starting from the node 1, it will start at this node and walk randomly through the graph searching for a Hamilton path. From the perspective of the algorithm, we are stuck now at node 9, and we have not visited all nodes in the graph exactly once. Therefore, we backtrack to the last node in our path and mark node 9 as unvisited. At node 2 we realize that there is no other adjacent nodes that can be visited from it, so we have to backtrack again. The same holds for the nodes 6, 3 and 5. At node 8 we realize that we could have visited another node instead of the node 5 in the earlier step. For example, we could have gone to node 7. But since node 7 has no unvisited nodes in its neighborhoods, we are stuck again at node 7. Following this, we backtrack again to node 8. The last possible path from node 8 would go over node 2. From node 2 we can go to node 9 and then we get stuck again. Therefore we backtrack to the last node in our path, which is the node 2. Instead of going from node 2 to node 9, we could have also tried to go over the other adjacent node of node 2, which is node 6. As always, we will backtrack now to the last node in the path that has unvisited nodes in its neighborhood. By now we have computed all paths that go from node 1 through node 4 into the graph, and none of these paths turned out to be a Hamilton path. The algorithm will proceed now in the same way through node 7. And now the conclusion would be that there is no Hamilton path starting from node 1 in this graph because we have simply checked all possible paths. The algorithm will try this procedure now systematically with other starting nodes. And even though the algorithm behaves similarly when started with node 2 or node 3, it finds a Hamilton path immediately when started with node 4. As you've seen, the backtracking algorithm can take a very long time because it tries all possible paths until it finds a Hamilton path if one exists. The main issue with this algorithm becomes clearly visible when considering its application on the following graph. Once the algorithm starts, it immediately runs deep into the graph and performs its backtracking approach if it gets stuck. In this case, this is unfortunately totally unnecessary, since it will not find a Hamilton path until it uses the node on the right here. Note that this graph has very few edges, and yet the algorithm already took very long. Now imagine how many paths it would have to check on the knights graph. The animation here on a small 5x5 knights graph took already that long that I can only show a small cutout. In summary, we can say that our first two approaches, brute force and backtracking, are in some sense not satisfactory. And although one can use them to compute knights tours on small chessboards, things change dramatically as the chessboard size increases. In 1823, H.C. von Warnsdorff published a paper entitled Des Rüsselsprunges einfachste und allgemeinste Lösung, which translates to the Knight's Tour's simplest and most general solution, where he introduced the method to find a Knight's Tour in many cases. This brings us to our third approach, known as Warnsdorff's algorithm. Warnsdorff's algorithm follows an intuitive approach. It is a so-called greedy heuristic. Greedy algorithms are algorithms that do in every iteration what seems to be optimal at the moment, without taking into consideration that this could lead to suboptimal results later on. Warnsdorff's idea is to always count the possible moves from all reachable squares for the knight and to move them to the square where this number is minimal. This is considered greedy because it selects in every step the square that seems to be the best choice at the moment. In fact, there's no guarantee that this algorithm will succeed in general, but you will see later that it performs surprisingly well on the knight's graph. But why is moving to a square with few follow-up moves even a good strategy for finding a knight's tour? Note that a node with a low degree in the knight's graph has few neighbors and therefore fewer opportunities to be visited later in the path. Now consider for example the situation from before. Before the knight made its second step here, we observed that the reachable squares or nodes had degrees of 3, 3, 3, 3 and 1. And if we had not moved to the square with the one follow-up move in this step, it would have become very difficult to reach that one later on. Moreover, there would be no follow-up move from this square if we reach it later from its only reachable square. In other words, we will get stuck if we move to that square later on. Just take a look at the following tour that behaves contrary to Warnsdorff's rule. Warnsdorff's algorithm demonstrates the power that heuristics can have, as it successfully finds a knight's tour in a vast number of cases, even on much larger chessboards. And as you see in the animation, it's not like this approach will only succeed on square boards. Even on rectangular boards it's often successful. And also the 64 knights tours shown previously were all computed using Warnsdorff's algorithm. A knight's tour is a Hamilton path in a corresponding knight's graph. And since this algorithm appears to be so successful, it might make sense to translate this algorithm into a graph theory setting to compute Hamilton paths in general graphs. This could make computing Hamilton paths much more efficient than with backtracking. The first step when using Warnsdorff's algorithm on a graph is to initialize all nodes with their degrees. In this example, we will start our path from the node in the top left corner, which represents the node number 0 in the path. In the next step, we must move to the adjacent node from which the knight would have the fewest possible follow-up moves. And the number of follow-up moves of an adjacent node is obviously given by the degree of the adjacent node minus 1, since we always have to exclude the edge that goes back to the already visited node. The next node will be selected as the one with the smallest updated degree. If the updated degrees of the adjacent nodes coincide, then the choice is obviously free. Furthermore, it becomes clear here that there is not just one knight's tour that follows Warnsdorff's rule, there are many of them. In the next step, we consider again the degrees of all adjacent nodes of the currently processed nodes, decrement the degree of each such node by 1, and then we select the node where the updated degree is minimal as the next node in our path. The algorithm will continue now in exactly this manner. The main question that you should ask yourself now is how well does Warnsdorff's algorithm perform on an arbitrary graph? And you have to remember something here. The Hamilton path problem is NP-hard, and therefore you cannot expect to find a Hamilton path efficiently on an arbitrary graph. Given this, it's already clear that the algorithm will fail on some specific graphs. In the background you see a graph with a Hamilton path that has been computed using backtracking. If we assume that Warnsdorff's algorithm works correctly, it should also produce a Hamilton path when started with the same starting node as in the above path. But this is unfortunately not the case. In the first step of the algorithm, we consider all neighboring nodes of the starting node, decrement the degree of each such node by 1, and then we move to the node where the number of follow-up moves is minimal. In this case, the graph is designed in such a way that Warnsdorff's algorithm fails immediately after the first step. But as mentioned before, this is not surprising, since the Hamilton path problem is NP-complete and therefore NP-hard. In general, it can be very useful to combine approaches. Let's say for instance that you start Warnsdorff's algorithm and get stuck at a dead end. Instead of generating a totally new tour, you can backtrack now to the previous square in the tour and continue with another Warnsdorff's tour. If you get stuck again, you can proceed with backtracking again, and so on. Another idea is to combine knight's tours to obtain new knight's tours on larger boards. Previously we observed, for instance, 64 different knight's tours on 8x8 boards. Now assume you're searching for a knight's tour on an 8x16 board. How can you use the already computed tours on the left to generate a knight's tour on this larger board? First of all, we can split our board into two 8x8 boards. Then we can search for a knight's tour on the left where the knight ends at a square that is at most one square away from the edge of the board. We can select, for instance, this tour here. Once selected, we can apply this tour on the left half of our chessboard. In the next step, we glue the boards back together and jump with the knight from the left over to the right board. And now we search for a knight's tour on an 8x8 board that starts from the current position of the knight and apply the corresponding tour on the right half of the board. A strategy like this that involves dividing a problem into smaller similar problems for which solutions are known, and to combine then these smaller solutions into one solution for the original problem is known as a divide, conquer and combine strategy. Of course, this can also be done with smaller boards and can be used to create knight's tours on boards with various sizes. So by now we've seen the most common approaches to compute a knight's tour, and from all of these, Warnsdorff's algorithm clearly stands out. But why exactly is the Warnsdorff's heuristic so efficient on the knight's graph? What makes the knight's graph so special? There's in particular one property that I want to discuss with you here in the following. And for this we need only one simple definition of a very famous number in graph theory. Many problems in graph theory involve coloring of graphs, and a famous number in this context is the chromatic number of a graph. The chromatic number is the smallest number of colors needed to color the nodes of a graph so that no two adjacent nodes share the same color. In this complete graph we can color for instance one node in red, and then we realize that there are still nodes with the same color in this graph that are adjacent to each other. Including the fact that every node here is connected to all possible other nodes, it is easy to see that the only way to color the nodes in this graph such that no two adjacent nodes share the same color is to color every node differently. In other words, for a complete graph, the chromatic number is equal to the number of its nodes. For another example, consider this graph. A coloring like this does not guarantee that no two nodes with the same color are adjacent. So we have to color differently. Moreover, it is not difficult to see that the chromatic number of this graph is indeed 2, because we have one node at the center that is connected to all other nodes and no further connections. Now let us take a look at the knight's graph. My first question to you is, what is the chromatic number of this graph? So the task here is to find the minimal number of colors needed to color the nodes in this graph such that no two nodes with the same color are connected to each other. Of course one can color always all nodes differently, but the question here refers to the minimal number of colors needed so that the mentioned property is maintained. This may sound difficult, and indeed the corresponding decision problem is NP-hard. But in this case you can easily answer the question by considering the coloring of a chessboard. It should also be clear to see that with every move of the knight moves to a square of a different color than the one before. So the chromatic number of the knight's graph is indeed 2. But wait a minute, if the nodes of a graph can be partitioned into two disjoint sets in such a way that no two nodes within the same set are adjacent, then it is called a bipartite graph. Therefore we can say that the knight's graph is also a bipartite graph, as every graph with a chromatic number of 2 is. Regarding bipartiteness, there are indeed many ways to check whether a graph has this property. In chapter 1 I mentioned that a cyclic graph is bipartite if and only if every cycle in the graph is even. Visually you can always pull the partitioned nodes of a bipartite graph apart as in the animation, where it becomes then clearly visible that connections exist only between different colored nodes. But the question of whether a graph is bipartite gives me here also the opportunity to show you how different mathematical fields can complement each other. We have here indeed a beautiful connection between graph theory and linear algebra, where one primarily focuses on matrices. And the famous matrix in graph theory is the adjacency matrix of a graph, which represents the connections between the nodes and which can indeed tell you whether a graph is bipartite. But how exactly should this be possible? Matrices have their own multiplication rule, and they serve in some sense as functions for vectors. When a matrix is multiplied with a vector, it can rotate or stretch the vector in various ways. For this specific matrix, we can analyze how it affects every vector in two-dimensional space. Here we notice that some vectors will retain their direction and will only be stretched by a specific vector. Such a vector v that does not change its direction when multiplied with the matrix A is called an eigenvector of the matrix A, and its stretching factor is then the corresponding eigenvalue. An n by n square matrix has always n many eigenvalues which are not necessarily unique. In the animation we've seen that the red vector 0, 1 has been stretched by a factor of 2 through the matrix multiplication. Therefore 2 is an eigenvalue of the matrix A, and the vector 0, 1 is the corresponding eigenvector. For those who don't know, it is common to normalize eigenvectors. The vector 0, 1 being an eigenvector of this matrix implies that all vectors pointing in the same or opposite direction are also eigenvectors of this matrix. All vectors that lie on this line here will obviously be stretched by a factor of 2 through a multiplication with this matrix. The matrix here has also another eigenvalue, which is 1. Furthermore, all vectors that lie on this line here will not be affected by a multiplication with this matrix because they are all eigenvectors to the eigenvalue 1. Now let us return to our Knights graph and calculate its adjacency matrix. If we compute now the eigenvalues of this matrix, we will notice something very interesting. The eigenvalues are somehow symmetric around 0. And now one might question whether the symmetry of the eigenvalues is merely a coincidence or if it gives further information about the graph. Furthermore, it turns out that if the eigenvalues of an adjacency matrix of a graph are symmetric around 0, then you know that you're dealing with a bipartite graph, which is in some sense fascinating. But additionally, it's also important to mention here that this holds only for simple graphs. So graphs without self-loops and without multiple edges between two nodes. But I think it's still a beautiful observation. Also very interesting are the eigenvalues of the adjacency matrices of complete graphs. The set of eigenvalues of the adjacency matrix of a complete graph with n many nodes always contains n-1 times the number -1 and then 1 time the number n-1. And don't forget that if a graph is bipartite, then its set of eigenvalues is always symmetric around 0. Now I will show you in a small bonus section how to actually implement Warnsdorff's rule in Python, as some of you have requested this through Instagram. The idea behind the implementation is to represent the chessboard as a matrix. At the beginning, every entry in the matrix is assigned the value -1. As soon as we reach a square, the number -1 there will be updated to the square's number in our tour. In particular, the code that we will discuss consists of two functions. One function generates the array that consists of the coordinates of all reachable squares for the knight, and another function creates a knight's tour through the application of Warnsdorff's rule. The function that generates the array containing the coordinates of all reachable squares for the knight is called position array. Note that this function receives the chessboard matrix and the starting coordinates as input. For the further computations, we save first the number of rows and the number of columns of the matrix. The arrays delta row and delta column are in some sense components of the vectors that must be added to the current position of the knight to reach a valid square according to its movement rule. In general, there are at most 8 positions to which a knight can move, and in the code they will be described by adding delta row of I, delta column of I to the current position of the knight, for I ranging from 0 to 7. Additionally, it is necessary to check whether any of the potentially reachable positions are outside of the chessboard. We save the coordinates of all reachable squares in the array reachable positions. In the following we check whether the row of a potential position is within the index range of the board, whether its column is within the index range of the board, and whether this position has not been visited yet, meaning the matrix value at this position is equal to -1. If all these conditions are fulfilled, the position can be added to the array reachable positions. Finally, we can return then the array. Now the implementation of Warnsdorff's algorithm. The function here is called toMatrix, and it receives as inputs the dimensions of the chessboard and the starting position of the knight. First we create a matrix with the dimensions of the chessboard, containing only -1s. The variable number counts the squares in our tour, and the starting square gets obviously the number 0. The next variable will be initialized with columns times rows -1. This number represents how often we have to select the next square according to Warnsdorff's rule. In the next line we enter the for loop, and here we have to compute in every iteration the possible positions from the current position row column, which will be stored in the variable reachable positions. To find the position of the square with the fewest follow-up moves, we start by setting minimum to the first element of the array reachable positions. Then we compute the length of position array for each element in reachable positions and update minimum if we have fewer follow-up moves from a square. The row of the next square in our tour is then given by minimum of 0 and the column by minimum of 1. This is an important step, because we update the variables row and column here and repeats the procedure in every pass of the loop. In the next line we assign then number +1 to board of row column and increment then number by 1. And finally we return then the matrix. For those of you who want to visualize their own Knights tours, I've decided to make the code to visualize a Warnsdorff's Knights tour available. You can download the code along with the corresponding Knight image through the link in the description. Note that I drew all chess pieces by myself, so that you don't have to worry about copyright problems. I wish you much fun with the code. See you in the next video.